Hello everyone, I welcome you all to the course of heat transfer. In today's session, we will discuss another concept, that is boiling and condensation. From the basics, you all know that boiling occurs when the temperature exceeds the saturation temperature for a given pressure. In the same way, evaporation occurs if the pressure is less than the vapor pressure for a given temperature. Evaporation is a liquid vapor interface phenomena, whereas boiling is a solid liquid interface phenomena. If we consider the classification of boiling, there are two types of boiling. One is full boiling, and the one is slow boiling. In case of full boiling, there will not be bulk fluid flow, and whatever fluid motion occurs, it is out of natural convection, that too under the influence of buoyancy. Whereas in case of slow boiling, there will be a bulk fluid flow, and this is caused due to forced convection by use of some external agent. It could be pump or blower or fan, etc. Now this graph indicates different regimes of pool boiling. As we have discussed, pool boiling is nothing but there will not be a bulk flow of the fluid. To make it clear, if you consider a vessel and put some water into it, if you start heating the vessel, obviously the water will also get heated. Now if you consider here, there is no flow of fluid except the natural convection, in which case the water which is at the bottom of the surface will catch heat, and the volume of that water molecule will increase. As a result, it will lose the density, and this will set up the natural convective flow. Whereas in case of slow boiling, we may use some pump in order to circulate the fluid through the hot pipes, where the movement of the molecules of the water are influenced by external agent. That is the main difference between cool boiling as well as slow boiling. Now in the figure, we can see there are four different regimes of the boiling. First one is a natural convection boiling, nucleate boiling, transition boiling, pelvic boiling. In the graph, along y-axis, we have heat flux, and along x-axis, we have excess temperature, which is the difference between superheated temperature and saturation temperature. Now, if you consider at this point, the excess temperature is 5. It means that the temperature at this point is 5 degree more than the saturation temperature. At this point, 10 degree more than the saturation temperature. Now, this graph is drawn at atmospheric pressure of 1 bar. Now, corresponding to atmospheric pressure, the boiling point or the saturation temperature for water is 100 degrees Celsius. We know this. For the first time, it was conducted by a Nicemia in 1934 under controlled temperature conditions. Now, he first demonstrated an experiment in order to understand the heat flux with respect to excess temperature. Let us understand the different regimes and what happens to the water when we start heating it. As I said, we will consider a vessel in which we will pour some water and we will start heating it. Suppose the temperature which is in contact with the water attains a value of say 103 degrees Celsius, then the water which is in contact with the material will absorb heat. As a result, the density of that water molecule will come down and it will flow towards the top. So this kind of phenomena can be seen up to a temperature of around 5 degree excess temperature. It means if you consider the saturation temperature to be 100 and the surface temperature is 5 degree more than the saturation temperature, which results in 105 degrees Celsius. At this point, 10 degree more than the saturation temperature, which is 110 degree Celsius. So if we go beyond saturation temperature, that is called as superheated temperature. You all know this from the basics of thermodynamics. Now, up to 5 degrees Celsius, there will be a natural flow of the fluid by losing its density and the fluid which is at the top will be having a lesser temperature. As a result, it will have higher density. Hence, the top fluid will move towards the lower part of the vessel. Now, from point A to point B, if the excess temperature keeps on increasing, you can see a small bubble will form, which will move towards the free surface of the liquid. The heat transfer or the heat flux from point A to point B, if you consider the slope, it is steeper compared to point B to point C. A point C is called as maximum heat flux. It is also called as critical heat flux. After point C, there will be a drop in heat flux, which is because of the resistance created by the bubbles. If you consider a constant heating, you can see here the bubbles have formed all along the surface, which will lift the water off the surface, precisely the bottom surface. Now at this point, the air bubble that has formed, it acts as an insulator and it increases the resistance. As a result, the heat flux will come down because we know that resistance is inversely proportional to heat flux. If resistance is increased, the heat flux has to come down. If the temperature is even increased, we will come to a minimum value of heat flux, say around an excess temperature of 120 degrees Celsius. We will encounter a minimum heat flux. That point is called as Leadenfrost point. The maximum heat flux point is also called as critical heat flux point. After point D, there will be again increase in the heat flux. This is because once the fluid lifts off from the surface, the air bubbles that will form, they will start radiating the energy. Now when radiation comes into picture, again the temperature of the water increases and it will follow the curve as shown in the figure. Now from origin to A, we can categorize this as a natural convection boiling, wherein the excess temperature is around 5 degree. From 5 degree to 30 degree excess temperature, we can categorize this as nucleate boiling, wherein a small bubbles of water vapor will form and they will move to the top surface of the fluid. Now, transition boiling is a region where there is a sudden drop in the heat flux in the range of 30 to 120 degree excess temperature. The lowest heat flux point is termed as Liddenfrost point, and the highest heat flux point is termed as critical heat flux point. After point D, we come across a film boiling where a film of air bubbles or air layer will form at the bottom surface of the vessel, which will start radiating with the increase in heat transfer, which will eventually increases the heat flux. Now this is a very important question that you can expect in your final examination. The same has been explained here. In case of natural convection, where you can see an excess temperature from 2 to 6 degrees Celsius, the fluid motion is governed by natural convection currents, and the heat transfer from the heating surface to the fluid is out of natural convection. Now this is what the nucleate boiling, where you can see a lot of droplets forming and they keep moving towards the free surface. Again, we can categorize from point A to point B as isolated bubbles, from point B to point C as numerous continuous columns of vapor in the liquid. It means that if the excess temperature is well within 10 degrees Celsius, you can see the formation of bubbles and they will move towards the free surface without disturbing the other fluid molecules. Whereas from point B to point C, the excess temperature is in the range of 10 to 30 degrees Celsius. At this point, you can see a numerous water droplets will form, which will continuously rise towards the free surface. And once the heat flux reaches a maximum value, that is called as critical heat flux or maximum heat flux. Now, this is what the transition boiling Now, if you see, a layer of water bubble has formed at the bottom surface, which acts as a resistance for the heat transfer. If this thickness increases, we have seen L over Ka, the thermal conductivity of this vapor is less, hence it acts as an insulator which will decreases the heat flux. That is why there is a drop of heat flux point from point C to point D. Now this could be in the range of 30 to 120 degree excess temperature. Now the excess temperature is nothing but how much temperature it is more than the saturation temperature. I'll repeat, this graph is obtained considering the pressure to be atmospheric pressure. So the saturation temperature corresponding to atmospheric pressure for water is 100 degrees Celsius. Once we reach the lowest heat flux point, which is Leadenfrost point, after that there will be a radiation mode of heat transfer which will increase the heat flux from minimum value back to the higher value. With this, I will stop here. In next class, we will discuss a couple of problems related to this topic. Thank you.